Quantum computing. Hi, I'm Ruan Rajapaksha. Quantum computers are lately gaining a lot of publicity and a lot of interest is there. Many companies are working on it. A lot of claims have been made that things would be very fast with quantum computers in the future. But so far, still on experimental stage. But let me give you an example to get your interest to see what quantum computers are all about. So let's say there is a black box here. It's an orange box, but let's call it a black box here. And there are 4 possible operations are possible with this black box. So operation 1 is flip. So if you send 1, it would flip it and it would give 0. And operation 2 is identity. That would be if you send 1, it's not going to flip it, it's just going to give 1. If you send 0, it's not going to flip it, it's just going to give 0. So these are reversible operations, which I'm going to discuss later, and they belong to category 1. And then you have category 2 operations, non-reversible. Operation 3, it's constant 0. No matter what you send, whether you could send 1 or 0, it's just going to give 0. It's not going to flip, it's not going to do anything, it just gives 0. Operation 4 is constant 1. No matter what you send, it's going to give out 1. So there are 2 categories. Now this is the question. Listen carefully. The question is, how many passes minimum? How many passes in minimum that you need to send to find out the operation belongs to category 1 or category 2? So let me repeat that. How many passes you need to send to find out not the operation, but we just want to know the operation belongs to category 1 or category 2. We just want to know the category. So can you do it in 1 pass? Let's see. So let's say we send 0 and it gives 0. Let's say we send 0 and it gives 0. So operation 1 is flip. So if we send 0, it will flip if it's operation 1. So it will give 1. So it gave 0, so it's not operation 1. Now let's see operation 2. So we sent 0, it gave 0, so it can be operation 2. So 1 we ruled out, operation 2 is a possibility. And let's see 3. Constant 0. It can be constant 0 also, because whatever we send is just going to get 0. And operation 4 is constant 1. It cannot be constant 1 because we sent 0 and it gave 0, so 4 is ruled out. So we are ruling out operation 1 and 4 in 1 pass. But we cannot tell from 1 pass whether it belongs to category 1 or category 2. We cannot do that. There's no way you could do with regular computers whether from 1 pass whether the operation belongs to category 1 or category 2. So to figure out, so we have to send the second time. Let's say we send second time 1 and it gave 0. So we said in this case we ruled out operation 1 and operation 4. So it has to be operation 2 or 3. So we send 1 and it gave 0. So let's look at operation 2. So it's identity. That means if we send 1, it will have to give 1. So it's not 2. So it has to be 3. So you need at least 2 passes to figure out the operation belongs to category 1 or category 2. But this is the deal. In quantum computers, you could do this in 1 shot, in 1 operation. That's the marvelous thing about quantum computers. It's very difficult to get it done. You have a lot of problems which we would discuss down the road, but that's the beauty of it. So now I have rekindled your interest. So I would assume you would want to follow this course and see how it's been done and what's the big deal about quantum computing. So let us look at this course, let us look at the table of contents. So first we are going to study quantum mechanics, introduction to quantum computing, which I already did kind of. And the double slit experiment. What does that do? Double slit experiment is where you send light and then it shows interference pattern. And so the behavior of light in wave form, light behaves in a wave, as a wave. So that's what was established. And then we will look at Planck's constant and the Blackbody radiation. The Planck's experiments, energy equals Planck's constant times mu. So we would do that. And then Schrodinger equation, Schrodinger's cat, everybody heard of that, the superposition, the wave function that basically Schrodinger wave function was the main function for long time until Dirac came along. And then we will talk about the fundamental particles in nature, leptons, quarks, and gauge bosons. There are 3 types of particles, leptons, quarks, they are called fermions, and the gauge bosons. Leptons are electrons and muons, and tau particle, and the quarks, there are 6 quarks, and the gauge bosons, there's W and M, and the graviton particles. So they are force carriers. Now we will look at what ultraviolet catastrophe is. There was a problem with ultraviolet and how that came into the picture. Heisenberg uncensored principle is very important that we would discuss. And some quantum computers are based on photons. Photons are light particles, and so we need to know about the photon polarization. And some quantum computers are based on electrons, and then they do their computations using electron spin. And if it's a quantum computer based on light photons, then it would be doing it based on polarization. And then we will talk about Einstein, Rosen, Podolsky, EPR paradox. This is where, for the first time, that Einstein started to question the concepts that were there at that time, the superposition and entanglement. He came up with a thought experiment where he showed that the entanglement has to pass information faster than light. That is called the breaking of locality, non-locality. So we would look into that, what EPR means. And Einstein said that quantum mechanics is not complete because there has to be some hidden variables, according to Einstein. And then later John Bell looked into this and he showed that there cannot be hidden variables. It's simply something that beyond our intuition. It's not, if you go back to Schrodinger's cat is dead or alive, is not, it is 50% dead or 50%, that's how we do math, but in reality, nobody knows. Nobody knows what state of the cat is. So that's what Bell showed, and it's very interesting. It's a very, very interesting experiment. So we will discuss the quantum superposition because that is being used in quantum computing, and entanglement. These two are the ones that quantum computers use. So, and then I will talk in many situations. People discuss quantum computing or quantum mechanics using a coin toss. But I will discuss why it is wrong to discuss. It's a wrong example to give for quantum superposition. It is very wrong. But for mathematical computations, if you throw in a coin and it's 50% head and 50% tails, and same with the electron, the way you have the spin up or down, but the internal mechanics is totally wrong, totally different. So that's what I'm going to say. But if you're looking for mathematics or what we see end of the day, then it's okay. And then we will mathematics background needed, complex numbers. You need to know the complex conjugate and its operations. And then the vectors, you have Bra and Ket vectors. They will be used in matrices. So you need to know the Hermitian matrix. And the matrix operations are done, they call it tensors. So you need to have the tensor product. So this is the mathematical background you need. And once you do that, we could go to the C bits and the C naught operation and the Q bit and the Q bit operations. And the Hadamard gate is what quantum computing is using. And then we would look into Deutsch-Jozsa algorithm. And that's what we discuss here, that how to do this in one shot. And that's Deutsch-Jozsa algorithm. So that's basic outline. It's a extensive course. I think there are like 30 lessons for the whole course, and I hope you would enjoy it. Thanks for listening.